Hello all, welcome back to operating system course. So today we will get started with the second type of memory allocation, that is non-contiguous memory allocation. So here we will be seeing paging and segmentation. So first let's get started with paging. Okay. So as we all know, paging is a memory management scheme that permits the physical address space process to be non-contiguous. That means if suppose you consider this as your main memory. Okay, we will have your operating system, right? Then say suppose you have a process P1, say it is of 5 MB. Okay, so in the contiguous what we had done, so entire process P1 was kept like this one, right? So each partition or your main memory was partitioned into equal sized partitions. So here, and the process has to be contiguous, but here what we will do, the process it can be non-contiguous. That means say suppose your process, or say suppose your memory is divided something like this, then out of 5 MB your process P1 can be kept here. Say suppose 1 MB can be kept here, and say 2 MB can be kept here, right? This is again your process P1. Let's say, yeah, I'll extend this one. So you have again process P1, again 2 MB. So all together we have 2 plus 2 plus 1, that is 5 MB of process P1, but it has not been kept contiguously. So it is non-contiguous, right? So P1 half portion or 1 MB of P1 process P1 is here. Say suppose you have P2 here, then again P1 comes, then again P3, P2, something like this. That means your process is not kept continuously in the main memory, right? Now this paging, it avoids your external fragmentation, and the solution for external fragmentation, that is compaction. So as we don't have external fragmentation, even we do not need the compaction here. So external fragmentation we had seen in the contiguous memory allocation, right? So we had free memory chunks in the main memory, but we were not able to keep the entire process there. Why? Because the free memory spaces were non-contiguous. So that's a problem can be solved here. Why? Because even if you have free spaces scattered in the main memory, you can keep it. But the internal fragmentation problem, it will be existing in the paging. Say suppose our process P1 is of 5 MB. So we will have a concept called as pages and frames next. So in that what will be done is like your main memory would be divided into equal sized frames. Okay. So if suppose say we have 5 MB process, and suppose each of these blocks are of 1 MB. Say suppose these blocks are of 1 MB each, like these all blocks are 1 MB each, then we can keep this 5 MB. Say suppose it is like 2 MB here, 2 MB here, and 1 MB here. So in this case we have wasted 1 MB of this space which has been given to this particular process's page. Okay, so first let's see what is paging, or what are the things here. So as we all know, this is non-contiguous memory allocation, and basically what will be done in paging is like your secondary memory, right? That secondary memory would be divided, or the process basically which is kept in your secondary memory, that would be divided into multiple equal sized partitions that are called as pages. Okay, I'll repeat once again. So the process or the programs which you basically keep in your disk or the secondary memory, that will be divided into multiple equal sized portions, and that portions we call it as pages. Now each page be, it will be of equal size. Okay, so say suppose we have I'll draw here, we have process P1 which is in our secondary memory. Fine. So in the secondary memory, your process P1 will be divided into equal sized portions, and that portion we call it as pages, right? Here it is pages. Something, say suppose your process P1, it is your process P1. Now in the secondary memory, your process P1 will be divided into equal sized portions. Okay. So something like this, right? Now each portion we call it as a page. Okay, like if suppose this particular portion, if it is of 1 KB, then all of this will be 1 KB each. Okay, we also know that the process has to be kept in the main memory for the execution, right? So as like your secondary storage or the secondary memory, your main memory, it will also be divided. Okay, it will also be divided into equal sized portions or the partitions, which we call it as frames. I'll repeat once again. So your process which will be kept in the secondary memory or the disk is divided into multiple equal sized portions. That portion we call it as pages, and your physical memory or the main memory will also be divided into equal number of blocks or fixed size blocks that are called as frames. Okay, it is called as frames. Okay, say for example this is our main memory. Okay, I'll draw here. Say suppose this is our main memory and these are the say fixed size frames. Okay, so each one of these would be called as frames, like frame 1, frame 2, something like this, and these will be of equal size, again like 1 KB each. This is for example. Okay, so now how your process that would be kept in the main memory? So process will be in the secondary memory, so it has to be brought into the main memory for the execution, right? Now you have to understand here, each frame is also of the same size of your page. That is, your page size will be equal to the frame size. If the page size is 1 KB, then the frame size is also the 1 KB. Okay. Now we will understand how the process or the pages basically would be kept in the main memory. Say whenever I say, or we'll take this example. Okay, so if this is process P1 and say suppose this process P1 has 4 pages, like page 0, page 1, page 2 and page 3. Okay, so these are the pages in your secondary memory of the process P1. Now to execute this one, our CPU has to execute the instructions that are present in this P1, right? So to do that, this process P1 has to be in the main memory. So this is your main memory, right? So your process has pages, your main memory has frames. Okay. Now each page of your process has to be kept in the main memory so that its execution can be done by the CPU. Getting it? So for us, it is quite easy to understand that we have the secondary memory here, then secondary memory here, and we have the physical memory here. So we can say that page 0 is present in one of the addresses or one of the frames of the physical memory. But your operating system, what does it do is like it keeps track of this, like which page is present in which frame. So that particular mapping is kept in page table. Okay, your operating system has a page table. Now this page table, it gives an idea to the operating system that which page of that particular process is kept in which frame number in the main memory. Getting it? So let me explain you this particular diagram. Okay, so your page table, okay, it accepts you can see two fields over here, right? So the first one here, it is page number. It accepts page number as the input and it gives you frame number as output. Okay, so your page table has two parts. Okay, one is the page number and another one is the frame number. Okay, now how to read this particular page table? Say suppose your process P1, it has 4 pages, right? So page 0, page 1, page 2, page 3. Now what does this page table contain? It contains or it index the page number, right? So you can see here 0, 1, 2, 3, which is the page number. It is same as this number, right? You can see here, right? So page table, it has page number as the index. Fine. Now this 0 corresponding to that 0 we have 1, corresponding to 1 we have 4, 2, for 2 it is 3 and for 3 it is 7. Now what does this mean? Correct? So this means your page 0, right? This one, page 0 is kept in frame number 1 in the main memory. Then page 1, you can see here, is kept in the frame number 4 of the main memory. Page 2 is kept in frame number 3. Page 3 is kept in frame number 7. Now look into your physical memory or the main memory. just check the content of frame 1. This is your frame 1, right? This is your frame 1. What does it contain? Page 0. That means process 1's page 0 is present in frame number 1. Then page 1 is in the frame number 4. Just check here. This is frame number 4 and page 1 is its content. Page 2 is present in frame number 3. This one. Page 3 is present in frame number 7, which is this one. So this is how you have to read the page table. Okay. Each process will be divided into equal sized partitions that are called as pages. Then your main memory will also be divided into equal sized blocks that are called as frames. So your operating system, it has to understand that which page is kept in which frame, right? For that it makes use of the page table. Again, understand here, the page size and the frame size will be equal. If suppose each page is of 4 KB, then each frame is also of 4 KB. Getting it? So this is the basic concept of paging. Okay. Now let us see the paging hardware. Okay. So basically the address that are generated by your CPU is divided into two parts. Okay. So here you can see in this diagram. So CPU, it generates the logical address that would be divided into two parts. One is P, another one is D. So P is nothing but your page number. Okay, page hash is nothing but page number. And D is nothing but offset. Or we can say D as displacement. That means the line number within a particular page is your D. Okay, or we can say that location within the page is the offset or the displacement D. So say suppose you have a process P1, fine, and say suppose it has two pages, okay, page 0 and page 1. Now this page again can be divided into multiple parts, or a particular page will again have the instructions kept in that, right? So to access one particular instruction, we have to understand from the starting location or from the base location, it is present in which location. The range we have to understand here. If suppose this has load instruction, then we have add instruction, then again say suppose we have store instruction. So say suppose this store instruction is present at the location 4 inside a particular page. Okay, this is one page, this is another page. Each page contains a set of instructions to get the actual instructions. So we need to have some displacement or the offset. So to get this particular instructions location, we can make use of this offset. I'll talk about this again later. Okay, so first now we'll understand how you can generate physical address in the using paging, right? So basically your CPU, it generates the logical address. That particular logical address is divided into two parts. One is your page number P and another one is the offset or displacement D. Fine. So first what will happen is this page number is given as an input to your page table. Now what does your page table contains? Page table, it contains your values, right? Page numbers as the index, something like this. And it contains some frame numbers, right? So like frame number 5, 10, something like this, right? So whenever the CPU generates logical address, that particular logical address is divided to two parts. The page number is given as the input to the page table. Now for the corresponding page number, you will find out the frame number by looking into the page table. Then what will be done is that frame number will be added with this displacement. Understand here, frame number F, it will be added with the displacement that gives you the actual physical location of the particular instruction in the memory. Getting it? So this is your paging hardware. I'll repeat once again. So CPU generates logical address that would be divided into two parts, page number and the displacement. Page number is given as input to the page table. So by looking into the page number, which is the index, you will find out the corresponding frame numbers. So you take the frame numbers, then add it with the physical then add it with the displacement or the offset d, so that gives you the physical address, then it can be given to your memory management unit. Fine. So this is about your paging hardware. That's it for today. We'll conclude our session. Thank you.